observe galaxy clusters. So we have to connect these two quantities, okay? So what we measure, for example, we can have for redshift, we can have spectrography or photometry. So when in most of the data that we have concerning galaxy clusters, we mainly from the large surveys, we have the photometric redshift information. So we have to include this uncertainty source in our calculations. Another quantity is the multiplicity function, is this F here that I presented before. The multiplicity function, which is describe the nonlinear regime of the halo or closed formation. These results, we have the first one based on the analytical result, based on the spherical collapse from Price testing, but we have been using those results from numerical simulation, from anybody simulation, sorry. And we have, for example, Tinker 2008, Tinker et al., which provides a multiplicity function with 5% precision at redshift 0. This value, 2016, describe they study the universality of the multiplicity function and given the mass definition that you use, but because this depends on the mass definition, if you use the mean density or the critical mean density, virial density, so this can change a little bit, and even the halo finder that you use to determine these multiplicity function. For example, if you use the friends of friends, so spherical density, this also give you some difference in the results, different parameters of the multiplicity of the fitting function. So Bouquet 2016, they include baryon effects, for example, and they provide the multiplicity function for given mass definition. So we have this flexibility. And we have also the McClintock example. They use an emulator and provide 1% precision at redshift 0. And I mentioned these different multiplicity functions because, for example, for LSST era, we need now to use, we have to care about the multiplicity function up to this few percent level. So this is another thing that we have to take care. And another uncertainty source that we have to deal in classical cosmology, for example, we have to study the estimators of the cosmological parameters. For example, for cluster counts, we have carried out a study considering an infinite likelihood for cluster counts. So this is an example of likelihood that we use in X-ray and SZ and Sunev-Zeldovich surveys, let's say, so, or CVB surveys. So we have that even if you use a maximum likelihood approach, the estimators are not necessarily unbiased, okay, even if they are consistent. So we have a study for the cluster counts and likelihood. We have checked what is the deepness, what are the bias on some cosmological parameters. For instance, for the matter density, sigma 8, and also the dark energy equation of state, where we consider a constant equation of state, dark energy equation of state. So we performed different studies and analysis, and we observed that in some cases the bias can be relevant, the order of the size, about 50% of the size of the error bar. But when we combine cluster counts with other probes, let's say with CMB, the bias tends to 0. So In another study that we are carry on nowadays is a master project of a student. We are comparing the bias and the results actually that we obtain considering binary and unbinary likelihoods. Martin Mackley and we have started this analysis about 10 years ago, and we noticed that we obtain considerable difference between binary and unbinary likelihoods. Usually, the unbinary likelihoods provide more restricted confidence regions and more constrained confidence regions, and the bias on the estimators also differs a lot from these two methodologies, for example. Another feature that we have to consider in cluster analysis are the halo profiles, dark matter halo profiles, take into account inner and outer profiles, concentrations, flashback radius. So we have a lot of even astrophysical information here that are really interesting to explore for not only for cluster cosmology, but mainly for the study of the astrophysics of the cluster themselves. We have to take care about numerical precision, and this is what I'm going to focus in the end of my presentation. But before that, I'm going to talk about the less uncertainty source, which is the cluster mass, and this is the main source of uncertainty for cluster cosmology, because mass is not directly observable. So, and this is the biggest issue for us. So determining the relationships between survey observables and halo mass represents the most difficult and complex challenges for cluster cosmology. And for example, we have some mass proxies. From X-ray, you can use the total luminosity or the temperature or the thermal energy. From the millimetric, you also have the Compton parameter. From optical and near infrared, you can use the richness. Richness usually you can consider as the number of galaxies that belongs to a cluster. And the weak lensing shear. Here I put the shears, but you have different signal that from equilensing that you can measure from the optical surface. And not only weak lensing, but also strong lensing. Strong lensing has also been used to estimate cluster mass, and usually you also have the combination from strong and weak lensing. And for example, here I put the expression for one term of the unbinary cluster counts. So if you want to build a likelihood for cluster counts, you have to build this number density of now its cluster. This term here is the number density of clusters per photometric redshift and richness. And this is given in terms of the dark matter number density that we described previously, in terms of the Hubble function, the sigma, and so on. So here is how we can relate the number density of dark matter halos with the number density of galaxy clusters. And we have to take into account so the distribution, for example, of the photometric redshift, given the true redshift, we have to take into account the probability distribution of given a true richness, how this is related to the true mass, okay, of the dark matter halos. And here we have the probability distribution between the true richness and that we observe. This phi here, this function, is what we call the selection function. This takes into account the completeness and purity of our catalog. So to have the cluster number counts, this number density, we have to take into account all these features that comes from observations. Okay. Some methodologies that you can find about cluster cosmology and cluster mass estimate are the binary and unbinary likelihoods, as I mentioned to you. And to give an example, for binary cluster counts, here you also have to integrate over a photometric redshift bin and over a richness bin. So we will have at least other two integrals here to compute the number of cluster in given a redshift bin and a richness bin. Okay. So you can find in the literature binary and unbinary likelihoods for cluster counts. We have also the information about cluster clustering, and you can also combine cluster counts with cluster clustering. We also use these methodologies for mass calibration, because most of the time we are interested to constrain not just the cosmological parameters, but also to obtain the mass calibration. We also have this other methodology, what we call pseudo-cluster counts. And this is an unbinary likelihood when we don't know the selection function. So we introduced here this new methodology, this new likelihood to apply in this kind of situation. We also have the approximate Bayesian computation. This here in this work, we compare the unbinary cluster count with the ABC methodology. What is the as an example, when you have a case where you don't have a likelihood, or it's too difficult to build a likelihood, you can use the ABC method to explore the cosmological parameters given the cluster count information. Okay. Nowadays you also have different groups applying machine learning to study to obtain cluster mass estimation, or even an application in cosmology. I'm going to describe this plot later in more details. And so to perform this kind of analysis, you always find each work use a different library. So, and even most of the time, you are going to see that each group has their own library, their own codes. But now, as we are approaching OSST and Euclid era, we are going to have a large amount of data, and the percent level of error on the cosmological parameter constraints are going to be about a few percent. So we need now. I would like to say that it's mandatory to have public codes where we can compare the results, where anyone in the community can reproduce the results. This is something that it's not actually in cluster cosmology. This is really rare. So and strange, because in science it should be natural to be able to reproduce a result, an analysis. So, but now we are more and more getting these public libraries to dedicate to cosmology. And here I list a few of them: the Numerical Cosmology Library, the Core Cosmology Library, which has been developed by a group, many authors in the Dark Energy Science collaboration, but it's a public library. We have Colossus, which means structure tools, Cluster Toolkit. I don't know if Cluster Toolkit is going to be maintained and up to date. We have also SkyPy. So nowadays we have different libraries that the community can use and explore. For cluster cosmology or cluster mass estimation, we have to build some pipelines where we have to take care of the theoretical computation, as I showed you. We have to deal with the data, the external data. So, for example, why I am calling here the external data? Because this library does not have the tools to process the data. You have to provide a catalog directly, okay? So that's why I'm separating the external data. And we also have the tools to perform the statistical analysis themselves. So in NumCosmo, we provide some of the statistical tools, EMCE, Cobaya, and we have Cosmo MC, and we have also in the literature many other tools dedicated to perform statistical analysis. I'm going to talk about a little bit gravitational lensing too, because I was describing the terms and how can we build a likelihood for classical cosmology. And now I'm going to talk a little bit of gravitational lensing, because this is going to be the main information that we are going to use in for example, in LSST. Okay. So gravitational lensing, this plot, this figure here shows the Earth, us the observer. We have here galaxy clusters that will work as a lens, because here the background between the observer and the background, we have this galaxy, and here we are trying to observe this galaxy. So the light will travel, and the light rays that pass close to this galaxy cluster that is between the observer and the source is going to be distorted, and we are going to observe this background galaxy in a different position, okay, given this lensing effect. So why weak lensing or strong lensing, the gravitational lensing, is so important for cluster? Because gravitational lensing is the unique probe information that provides the information about the absolute mass of the galaxy cluster, because X-ray or Sunyaev-Zeldovich or other probes are sensitive to the gas astrophysics. So when we take a picture, let's say in X-ray from a galaxy cluster, the main information that we are getting is about the intercluster medium. The same for Sunyaev-Zeldovich. Okay, so in the richness, as I mentioned, the richness is about the galaxy that belongs to a galaxy cluster, but it corresponds to just 2% of the cluster. So gravitational lensing, otherwise, it provides an information when we measure a lensing quantity. This the shear, the surface mass density, the reduced shear, this information is telling us something about the absolute mass of the cluster. This is why it's so important, okay? And we have here, like for cluster cosmology, to obtain cluster mass estimation, we also have different methodologies. We have a stacked approach, where it's a methodology that you have to combine the signal from different clusters. And this is useful for clusters with smaller masses. So for masses smaller than 2 times 10 to 14 solar masses. And we have also some methodologies to obtain individual cluster mass. And this is useful. We can apply them for massive clusters. Okay. So as I mentioned, we have here the background galaxies. With the observer is going to observe these background galaxies distorted and magnified due to the presence of the lens, which In our case, it's going to be a galaxy cluster, okay? And we can measure the reduced shear given the ellipticities, and you have also to consider the point spread function, PSF effect in these measurements. So here I put the equation for the reduced shear, because usually this is a quantity that we use to obtain cluster-mass estimate, where beta, gamma, and kappa, I'm going to describe, beta, oh, sorry, beta is this ratio between the distance, the angular diameter distance between the lens and source, between observer and source, and so on. Here we have the convergence and the tangential shear in terms of the surface mass density. This relation here, where we use the surface mass density, is written in terms of the halo mass, the halo, dark matter halo profile, okay, matter profile. So this is another thing that we have to model, and you have, for example, most of you have heard about the Navarro-Frank-White profile, and this again, you use anybody simulations to study to fit a profile for these objects, and you have to different work has dedicated this kind of study to different range. So if you are interested more in galaxies or galaxy cluster, these scales are going to change a little bit these profiles and the parameters. And here we are going to use them in these calculations to compute clustering and to obtain some cluster mass estimation. So if we are going to use weak length signal, we have to enter with this information. So the tools, the libraries, CCL, Colossus, NumCosmo has to provide also this kind of quantities. Okay. Oh, sorry. Okay. So here's an example. You can access it in the CLMM. Sorry, this is a LSST desk plus a weak length mass modeling library for cosmology. We released the first version last year, so you can find here. And this is an example of cluster mass estimation using weak length signal. Here is just simulations, but we compare different methodologies. The blue curves are obtained using a binned likelihood, and the purple curves we obtain from an unbinned likelihood. Notice that these likelihoods that I mentioned here are not the one in terms of the cluster or halo number density, as I mentioned here, okay, because this we are going to apply to use for cluster cosmology, and we have other likelihoods to obtain this cluster mass estimation, but you can assess that. And as we obtain here for concentration and mass, this huge difference between binned and unbinned likelihoods, some similar results we also get for cluster cosmology when we study when we fit the cosmological parameters. And because the unbinned likelihood provides more information, you are able to use all the information of your catalog, let's say. And that's why we obtain this difference. This is here, we are losing some information when you compute some means, when you compute things in bins, okay? And here I'm going to start to present to you some comparisons that we are carrying out between some libraries such as NumCosmo and CCL. We also have some results comparing NumCosmo, CCL, and Colossus, and Cluster Toolkit also. And here are some examples for the mass function. We have here, I don't know if it's easy to see, in the upper panels, we show the mass function times the mass, okay? And here is the relative difference between the computations. We show here some multiplicity functions, the mass function using some different multiplicity functions, Prachester, Chatterton, Jenkins 2001, Tinker 2008, Tinker 2010. Here we have the results from Bouquet 2016, comparing different situations, because Bouquet is a multiplicity function where you can include some baryonic effects or not. So DM is for dark matter, and Hydro is for hydrodynamic simulations. And as I mentioned before, you can also use different mass definitions. So here we show the results considering the mass based on the mean density and the critical density, given an overdensity of 200, sorry, or 500. Okay, and the difference here is up to 10 to minus 4 between roughly the worst result is about 10 to minus 4 comparing these two libraries. Okay, and here I show in more detail something that I want to call your attention. You can see that here we put Tinker 2010 and Tinker 2008, but these comparisons were made considering delta density equal to 200, and the mean we were also considering the mass definition given by the mean density. But I would call your attention the reasons, because Tinker 2008 is a multiplicity function that are largely used in the literature. And here we show the comparison between CCL and NumCosmo for Tinker 2008 when you use the mass definition given by the critical density. So the results, and here, even where this is an update plot where we get a relative error of about 10 to minus 6 between CCL and NumCosmo, and this is considering the mass definition defined by the mean density. And here's the difference on the results when you consider the critical density. So I would call your attention, because you can use both, okay? But this huge difference between NumCosmo and CCL, and the same happens for Colossus, is because CCL and Colossus implements, computes this multiplicity function considering a linear interpolation, okay? Where NumCosmo uses the cubic interpolation, including the second derivatives information that's provided in Tinker's paper, okay? And here we also made this comparison, choosing CCL and Colossus to perform this computation using cubic interpolation, but the result is almost the same, because it's to get a better precision, you have to use the information of the second derivatives, okay? So this is something that I believe is really important, because in this case, we obtain something, the relative error of about 10 to minus 2, for example, in this region. This region is really important for classical cosmology. We have here 10 to 13, okay, solar masses. So this is the range relevant for cluster cosmology or cluster mass estimation. And here we have this kind of numerical discrepancy, okay? So this is a nice example how we have to take care and check and have different libraries and test these libraries and determine with what precision, what are the precision we are made our computations, okay? Another example, these we also explore in CLMM papers, so you can see more details there. Here we compare the surface mass density computed with NumCosmo, Colossus, and NumCosmo, CCL, and Cluster Toolkit here in this right panel for N-ISTO and Enrique's profiles, and the right panel for NFW, okay? And this, we show here, and this comparison were made NumCosmo, CCL, and ClusterQt compared with Colossus, and we have a great agreement between Colossus and NumCosmo, and not so well for ClusterQt and CCL, where in some range we get this 10 to minus 3 relative error between the libraries, okay? And this is something that you can always, for example, if you want to use CCL, you can go there and adjust some parameters, for example, of the interpolation method, increase the number of nodes and so on. I'm going to describe this here, where we compare the cluster number counts from, we are performing this study and comparing, cross-checking NumCosmo and CCL. We are considering unbinary and binary likelihoods, where we consider, for now, we are assuming spectroscopic redshift, but considering the richness mass proxies. And for this, we obtain a relative difference between the cluster, the number density, actually, the final result over, for example, we are considering a catalog with 12,000 clusters, and we are building this likelihood, and the relative difference that we obtain is 10 to minus 1 in the mass function if we use CCL with the 4 interpolation values. So if you increase the numbers of nodes, for example, and change some CCL interpolation parameters, we obtain a better precision, 10 to minus 4 to minus 4. It's what the example we are considering right now. But this has also a cost, because in this case of high precision, or what we are calling high precision, NumCosmo is about 100 times faster than CCL. For example, we compute this 12,000 elements, the number of clusters per redshift per richness, 2,000 terms like this takes about 0.4 seconds in using NumCosmo, but the same computation takes about 40 seconds in using CCL. So to conclude, as I mentioned, soon we are going to start having data from LSST and Euclid, where we are going to have a large amount of data, and we are reaching a few percent precision level on the cosmological parameters. And as I mentioned, it's mandatory that we have now well-tested libraries. We have clearly and available these kind of comparisons, and also each code has to clearly inform what is the precision of the computations, of the calculations, okay? And because we have different numerical errors, source of numerical errors, such as from interpolation, integration, and most libraries adjust these the parameters. For example, those that I mentioned to perform an interpolation for particular cosmologies. So it's not guaranteed that when you are performing, for example, IMC-MC analysis, that precision that you are assuming your code has, it's also really being attained if you are computing your functionality in another point of the parameter, the cosmological parameter space. This precision is not guaranteed. So you have to take care, much care about it, because otherwise we are going to start to have some spurious results on our cosmological analysis, okay? And for example, in NumCosmo, we take care of it. The user chooses the precision of each computation. So for example, if you want to compute the model distance modulus for supernovae analysis, you are going to say, okay, I want my theoretical computation being performed with this precision. And we are going to, you pass this information, and even in an MCMC chain analysis, this precision will be, you know that this precision is going to be attained, and this request will be attained for each step of your MCMC chain. So NumCosmo provides the safety, let's say, about the numerical computation. We are developing this desk project that is a project inside the Dark Energy Science Collaboration, where we are developing a set of Jupyter notebooks where we compare these different libraries, NumCosmo, CCL, Colossus. We are going to compare them with SkyPy, for example, or Cluster Toolkit. So some of these Jupyter notebooks are already available, distributed with NumCosmo, okay? And we are going to we are working to have all functionalities from both CCL and NumCosmo tested, cross-checked, verified, and public. These tests, all these tests also public. All these Jupyter notebooks public, is such that anyone can access. Here in the presentation, I focused on galaxy cluster analysis, but these libraries also, not all of them, but NumCosmo and CCL also provide functionalities to perform some analysis in large-scale structures, supernovae, CMB, and other cosmological probes. This work has been done in collaboration with Sandro Vitenti, Henrique Lettieri, Cynthia Nunes, Ana Caroline Manso, Céline Combé, Constantin Payer, and many other people, not only in desk, but outside also. Thank you so much for your attention, and please feel free to ask me anything.
Thank you, Mariana, for your magnificent talk. Lot of applause here. We have no time for a very short question. There are some here.
Hello, Mariana. Yes, so I assume you have worked within Lambda CDM cosmology, right? In your results and analysis. If this is the case, I would like if you could mention the recent tension or rise by the team of Piero Rosati about the so-called small-scale excess in strong lensing towards the center of galaxy clusters. I don't know if you know this science paper of 2020. They observed with the HST and VLT. I don't know if you could mention something about this.
And
or
about the excess of what? Sorry, I couldn't hear.
About the and the tension with respect to.
The sound is cutting a little bit. The tension between lambda CDM and
the observations of this so-called small-scale excess due to strong lensing.
Due to strong lensing. Oh no, I don't know the details.
Okay, so you mainly work with weak lensing in your analysis.
Yeah.
Okay.
Yeah. But I know strong lensing has been used to not just in combination with weak lensing information, but strong lensing itself alone is also used to constrain, to provide cluster mass estimation. But as mentioned, you talk something about small scales, because you have these, you have the galaxy cluster, so you have the background galaxies, let's say, and this weak lensing, strong lensing regime depends on the distance from you that I'm going to stop sharing because like this you can see me, I believe. You have observer, lens, and the background galaxies. So when you project on a plane, you have here the lens. You have the center of the lens. That's another problem to determine. You have to take into account miscentering correction, for example, in the computations that I mentioned here. You have the background galaxies depending on depending on the distance, everything project, the lens and the background galaxies, depending on the distance of the background galaxy to the center of the halo, you determine this strong lens and weak lens regime. So if you are close, I cannot give you a number. I don't know if you are, let's say, I don't know, 20% apart from the center, you are in a strong lensing regime, and outside these, you are in a weak lensing regime. So this is why, this is how you can combine both strong lensing and weak lensing information to provide this cluster-based estimation. But this tension that you mentioned, I don't know. I have to check what's the tension between lambda CDM and the results they got from strong lensing.
Okay, there's no more question. Okay, we thank Mariana for your amazing talk, and we'll continue with